So now let me introduce our speaker, Dr. Ted Urbancic. I'm going to read his little bio here. He's a founder of ESG and executive vice president of ESG's Global Energy Services. He has over 25 years of experience in examining and interpreting microseismicity associated with mining and petroleum applications. He is a pioneer in the development of microseismic monitoring in industrial applications and has written numerous publications ranging from understanding the fundamental aspects of microseismicity to characterizing rock and reservoir behavior by integrating microseismic data with numerical modeling and geomechanical data. Urbancic also holds expertise in various areas such as earthquake generation processes, earthquake rupture mechanics, source scaling behavior, and identification of failure mechanisms. His current focus include using seismic source techniques to assist in reservoir optimization, in the evaluation of hydraulic fracture simulations, and EOR activities. Urbancic holds a PhD in seismology from Queen's University, Kingston, Canada, MSc in Geophysics, and honorary BSc in Physics and Geology from the University of Toronto, and is a member of numerous professional societies, including SPE, SEG, AGU, SSA, and EAGE. So, welcome, Ted. And as you can see from the monitors for everybody, the title is Passing Seismic Monitoring of Hydraulic Fracture Stimulations. What have we learned from over a decade of monitoring? Take it away, Ted, and welcome.
If I knew you were going to read that out, I wouldn't have written that. Sorry for putting everyone through that. So I'm going to talk about hydraulic fracture stimulations, and it is a current topic of interest in not only the scientific world, but in the public domain, for a lot of different reasons, and I'll touch on some of those. The whole concept and idea of monitoring hydraulic fracture simulations, you think is something that would have happened a long time ago, but actually the monitoring of seismicity is fairly recent. In fact, in 2000, when ESG went out there, we did the first commercial hydraulic fracture stimulation monitoring program, what I call the current era. And it's from that things have moved forward quite tremendously. So today I'm going to go through where we started from, some of the initial concepts and ideas back in around 2000, late 1990s and 2000s, and to where we are now in terms of our understanding of hydraulic fracture stimulations and what's actually going on. So the whole concept of hydraulic fracturing is basically you go in and you fracture a rock. Well, the early assumptions were fairly basic. I mean, rock is homogeneous mass, no pre-existing structures. I mean, that was something that hydraulic fracture engineers would look at and say, there are no fractures in our reservoir. It's one solid piece of rock. Hydraulic stimulation nucleates fractures which propagate through the rock, and they grow symmetrically about a treatment zone. So if you think of a well, they'll put a treatment well in, and they'll put proppants and all sorts of fluids into that hole to try and fracture the rock. And magically, all those fractures grow symmetrically about that well. In fact, they form almost an elliptical shape around that well because they're all vertical to subvertical fractures. So that was a concept and the idea that was discussed and been behind hydraulic fracture for many years, up until around the 2000s, around 2000. And even today, there are a lot of people who still believe that all fractures grow symmetrically about a treatment well, and they're vertical to subvertical. So like I said, in around 2000, microseismics came on the scene. And actually, really, it had been tried for many years before, back into the 60s and 70s on an off basis here and there. No real substantial effort was put into trying to understand what these small, effectively are micro-earthquakes that are being generated, what they could mean in terms of the hydraulic fracture stimulation program itself. In 1997, the oil industry created a consortium called the Cotton Valley Consortium, and there were 3 of the largest oil companies in the U.S. got together and basically tried to monitor using microseismicity some hydraulic fracture stimulations. And it was the first instance of showing that there could be some value added to the stimulation program in terms of understanding what was going on by monitoring microseismicity. So by 2000, those initial challenges were being looked at in terms of the assumptions that are listed above, the early assumptions. That fracks not always grow symmetrically. Changes in treatment programs and completion styles can affect fracture growth, and not all fractures are vertical. And yes, there are such things as pre-existing fractures in reservoir, and they could have an effect in terms of what you see. These are all new concepts to the industry that went into the face of their understanding of how things were progressive doing stimulations. So today I'm just going to talk about this evolution of microseismic monitoring, where we started from in the late 1990s and where we are now in terms of trying to understand how reservoirs are behaving and actually put the foundation of where we're going to go from here. So again, the early days, single vertical offset observation wells. So you basically had a well that you're going to treat, and you pump your fluids and your proppants and that into to try and fracture, and you'd have another well offset from that one that would you put instrumentation in. So you put in a series of geophones, typically 15 hertz, so high frequency geophones into that well, and that would be your monitoring well. All microseismicity is small, so the magnitudes for these events would be less than zero. So that's why you have these high frequency geophones. And basically what we're after is the dimensions, the length, the fracture height, the orientation of the actual fracture. Remember, we're dealing with a planar symmetrical fracture about the treatment well. So the simplest thing you could do then is, if you saw some seismicity, is draw a box or an envelope around the events, and that would then assess from that, you would assess the actual volume that's being stimulated. So that would then be the stimulated volume. And of course, stimulated volume is then equal to production. So that's the earliest ideas, the early days of monitoring. And so, of course, more events equals more production. And the only reason for using microseismic monitoring was geohazard layers. So a lot of the reservoirs, you have water-bearing layers, you want to stay away from them. And if you start fracturing in a reservoir and you start seeing events migrating toward these geohazards, it's potential to stop that process. If you stop it, you can save yourself millions of dollars. So I'm going back here. Here's the early days. Here's a fracture variability, the Barnett Shale in 2000. So in one field, we did, 12 different stimulations. And it may be hard to see back there, but the blue dots here, it's a vertical well, it's all in plan view. The blue dot is the monitoring well. The red here is the treatment well. And so in the field, and you're talking about fractures that were literally within a few hundred meters to a kilometer apart, the response you can see is quite variable. The response that they were thinking that they would have is this one here. And you can see it pretty much that you have effectively a symmetric type response around the treatment well. And the growth of that fracture is along the maximum horizontal stress orientation. So that's what they expected for all the treatments. But when you start looking around, you can see that sometimes they're asymmetric. Sometimes the actual stimulation went right towards the observation well. And then you ended up with this sort of complex sort of pattern. And if you actually follow it, you can almost see that there's a series of subparallel lines and crossing lines. So you have a series of faults. So they stimulated into faults and cross faults, and all the stimulant went along those directions. So all the green dots are just showing the event distribution. So now you're going to try and put a volume around this and say, this is your stimulated volume. Well, the first thing you have to get your head around is that, well, the fractures are symmetric. The next thing you have to say is that maybe structure has a play. Back in 2000, we went to a company called Mitchell Energy, and we went in there and made this presentation. And the VP of Mitchell basically stood up and said that this is all hogwash, this is impossible, because they have no fractures in the reservoir. And when they actually brought a geologist in, he basically looked at the distribution of the events and said, that's the distribution of fractures we have in our major faults and fractures we have in our reservoir. So it really is, it started to give information that we didn't have in terms of understanding what the stimulation was actually doing. All their models were based on this symmetric type fracture, but in fact, all the patterns were quite different. and depending on where you were in the field, you have a different response. So what did that mean in terms of the actual production? Well, if I look on the right, here's your symmetric fracture that everybody was looking to have. And this on the bottom is the actual production, days after the treatment on the bottom. So within a year, you can see there's a decline in production, and that's called the decline curve. And this is actually what normally a decline curve looks like. So it looks pretty normal for symmetric fracture. But for the complex fracture network, what you see is quite a different pattern. And you see that they had, over that 1 year, very high production all the way through, and continued production. In fact, that well produced well for a number of years afterwards. And so all of a sudden, the whole structure as to how you're fracking or why you're doing it changed, or the underlying philosophy changed. You actually want to intersect these fractures. You want to know where these fractures are. You want to be able to understand their orientations, their dimensions. You want to be able to look at it and be able to say and target them so that you can actually use them as part of the stimulation program. The more pathways you can create by intersecting fractures back to the treatment well, the more production is possible. So the whole approach started to change. But if you have fractures, then you want to be able to understand those fractures. And to understand those fractures means that you have to have a better distribution of sensors around the volume, around your target volume. So one of the things that started happening by the mid-2000s was a move away from one single array type monitoring. With a single array, you lose the ability to get good coverage around the target volume and the ability to really understand that stimulation program. So we started moving into these sort of configurations. Multiple horizontal or vertical arrays. So here we have 3 arrays. Look at the screen here, 3 arrays. And you have an event, a treatment well, and you can see all the array paths going to the various sensors. These are all sensors in the well. And so you have a very good coverage of that volume 3-dimensionally. That means you can use that information to backtrack out more about the actual source that created that, generated that seismic signal. You can do things like moving into a vertical and into a horizontal array configuration. That was, again, one of the big changes in the mid-2000s is understanding you want to target more of the reservoir. It meant moving away from a vertical array to horizontal arrays. And by using these horizontal arrays, you can actually get more coverage throughout the actual reservoir. So by putting the sensors down horizontal arrays, you now have the ability to be able to see larger volumes. And then, of course, adding sensors near surface. And by adding sensors at surface, near surface, you can start looking at larger events. So very much akin to earthquake seismology, we're doing the same thing here. You can add sensors to look at larger events. Still, this part did not materialize so much later. This sort of multi-array configuration type work started really proving itself in terms of understanding what's going on. So the challenges to the old ideas meant we had to look at things like how do fractures initiate and propagate? Are new fractures being created or are old fractures being activated? What is the role of pre-existing fractures and bedding planes? If anyone goes to an outcrop and looks at the outcrop, there are a lot of bedding planes there. And so do they actually play a role? Are these fractures open or cemented prior to stimulation? Or are some fracture sets preferentially activated during stimulation? And what interaction of fractures, what is the interaction of fractures in different mutations? So the concept of a single fracture is now being questioned. So we started bridging that gap in understanding by looking at more details of seismicity. So in this slide here, we can start off here. Here's your typical waveforms that we're seeing down below. You probably can't see it from back there, but there's actually 3 traces on every single one here, 3 colors, and each one of these represents a triaxial sensor. And so we have the 3 components mapped out. From that, we can get amplitude information, we can get phase information, we can get polarity information, we can get duration information, all the normal things that we get out of any sort of seismic signal. And we can use that and look at it in the frequency domain. And there's some interesting things associated with that. Here's a frequency spectrum that we get. This is in black is the noise. The decay slope, which is related to attenuation, is effectively a -2 slope. And we fit that. And we fit that with what's called a broom model fit. It's basically a penny-shaped crack model that we apply to it. And the fit's pretty good. And we can use that fit to describe the actual source rupture process that's going on. So this plateau here, we relate back to the seismic moment, the strength of the event, the magnitude. The corner frequency here, which is breakoff plate, right there, can be related back to the rupture duration. And that rupture duration between initiation and the final time of rupture can be then related back to dimension. Again, thinking of a penny-shaped crack type failure. And so we can get dimensions of the actual rupture surface itself. If we have enough coverage, say multi-well coverage, we can look at the intersection of all those ray paths for every one of those signals through a focal sphere. And from that, work out the type of failure that was initiated the rupture itself. So if I look here on the right here, you have mode 1, mode 2 type failure processes. And from that, you'll get a different sort of distribution of motions and amplitudes over that focal sphere. So if I look here, this is a typical, what's referred to as a double couple or a shear type failure process. And these lines here, the red is the maximum principal strain orientation, and that's a minimum principal strain in blue. Of course, that allows you, if you have good coverage, to be able to assess other types of failure other than a shearing type failure. So if you have a mode of failure that's associated with opening component, as we see here, mode 1 failure, it'll be perpendicular to the minimum principal strain orientation, and you have a fracture plane that'll be perpendicular to that minimum principal strain orientation. And so you can work out an orientation, and you can work out the mechanism and the type of failures you have. And of course, you can have closure as well. So you can have a combination of these mechanisms, and from that be able to assess what type of failures it is that we're looking at. One way of looking at it is looking at something called a Hudson or KT plot. And in fact, if I look at the different types of failures you can have, in the middle here you have your shear type failure, the DC component, right there. And if you have like a frac opening or a tensile failure, it's going to map out up in the top left quadrant there. And if you have crack closure in the bottom. I also have in here some things like an explosive. So if the actual first motions and amplitudes are all positive, moving away from the source in every direction, it'd be like an explosion. And so that would map out at the top. And if it was implosive, like a pore collapse or something like that, it would map at the bottom implosive down here. There's an interesting one called a CLVD, and that's a component of failure referred to as a compensated linear vector dipole. And that is part of a tensile crack opening type process. So if I think about it, basically you take a tube of toothpaste and you squeeze it. So I basically have forces coming in from all directions in the plane. The resultant forces are out of the plane vertically. Or I could take that tube of toothpaste and squish it into a pancake. So my initial forces are along the axis of the toothpaste, and the resultant forces are all outwards in that plane. That is typically part of a crack opening or a crack closure process. So now we have the ability to look at these mechanisms, the failure processes associated with these individual events. And so what do we see? And this is a fairly complicated plot here because there's a lot of information. So what I have here in black is the actual treatment zone or treatment well. So this would be a horizontal well at depth that they're going to stimulate. I'm looking at a plan view, cross-sectional view, and a parallel view. And it's showing the various logic there. So this actual formation is the Horn River I believe this is Horn River in northeast British Columbia. So we're down about 6,500 feet. Here I'm going to plot what are effectively the poles to the planes that are being stimulated from every event. So every event, we determine a mechanism. From the mechanism, we determine what the orientation of fracture planes are, and from that get the pole to those fracture planes. And here's my KT plot. Down here in the bottom is the engineering data. And so we have mapped here things like the slurry rate and the carbon concentration in purple and the pressure in red. And I'm going to play this back in time so we can have a view and a sense of how things change during the stimulation. So it goes pretty quickly. And what you can see is in the early stages, and I'll play it back again, all the failures tend to be up in this quadrant. So we have a large tensile component of failure. And over time, depending on what the different types of compounds that they're putting into the ground, so here they're using 100 mesh versus 47 mesh sand. So the sand size that they're using changes. The sand size, basically, if they have a spacing that allows for a smaller or larger sand size to go through, is defined by the next size. So by playing it back again, you can see that initially you have all these tensile failures up in the top left quadrant. You can see that you have a particular orientation of failure. So that is showing a fracture set that's oriented northeast, southwest. And then I continue that process. And as we follow through, at some point here, you can see there's a transition. And a transition from one set of fractures that were northeast set fractures to a series of northwest fractures that are actually now closing. So during this process, you can actually map out what is going on based on the injection program that you have in place. And you can continue that. At this point here, you change changing the mesh size, and we're getting just pure shear type failures in the middle. So in fact, you can actually look at it and break it down by these different components, and you can see here in the different time intervals that I've taken, the A, B, C, D, and you can see the different types of failure processes that are observed. From being pure tensile or almost pure tensile crack opening to shear failures to a tensile crack opening to a variability between opening and closure. All these fractures have a shearing component associated with them. If you actually look closely at the KT plots, you look at the distribution of the lines, basically the way it's structured, you still have a shearing component of failure even though it looks like it's dominated by tensile. So these failures are shear tensile in nature, but they vary depending on how you actually inject into a program, into the ground. And that allows you then to start looking at how effective the stimulation program was itself. So in this stage here, in this case here, I can look at a whole series of stages. So this is again in northeastern British Columbia, and these are horizontal wells. And each of these colored zones is actually a treatment zone. They're called perf zones, and that's where you actually stimulate one after another. And in fact, they do something called a zipper frac. You go from one stage across to the other, and back and forth across the various wells. And each time they do that, you have basically a series of events. So here, this blue zone here associated with that treatment, there's a series of events, and that defines the extent of fracturing. Sometimes, depending on how close these wells are spaced to each other, these stages are spaced to each other, you have overlapping events. If you can understand the failure process associated with these, you can understand whether they can actually contribute eventually to production or not. What you'd like to have is a series of fractures that are open and stay open. If they start closing, it actually closes off a potential pathway for back to the treatment well for production. So if I look at it here closely, through the various stages, you can see that basically most of them are tensile crack opening dominated failure processes. Here though, in stage 17, it's showing that we're starting to close a lot of those fractures. And so what it's saying is that the staging of these fractures, the stimulations, are too close in that case. What you don't want to have happen is a closure of those existing fractures. So it gives you a sense that you can use this data to really understand the process of the engineering process that's taking place. So we start off with a series of event locations. These are a series of events that are picked up. You can do all these inversions to get the actual mechanisms associated with the failures. And again, by looking at the orientation of the strain axes as well as the type of failures, we can work out what is effectively the discrete fracture network. This would be the distribution of the actual fractures that are being stimulated in the reservoir. And here I've actually put a series of them showing for the same events that are sized based on the penny-shaped crack model. So we have a dimension associated with that, and color-coded based on the type of crack opening component that's associated with it. So if it's actually an opening fracture, it's going to have a warm color, like the red colors there. And if it's actually a fracture that's closing, it's going to be a cool color, like the blue colors there. So you can see that you have quite a variety, and you can start assessing, instead of a series of dots, you can start assessing what these fractures are actually doing. You have fractures that are sub-horizontal, you are sub-vertical, so this is looking into the plane, cross-sectional view, and it's again a sub-vertical one, but you have quite a few of these sub-horizontal ones, and they may be associated with things like bed and pin failures. You have areas in stimulation where you have warmer colors. Those are areas where you're effectively opening up those fractures. And that's probably where you're going to get your production from. Where areas where you have more cooler colors, more of the blues, you're probably not going to get production from those areas. So now you can start looking at, instead of putting an envelope around a volume of events and saying, that is where my stimulation has occurred, and that's where I can see production going to come from, you can actually go in and start defining sub-volumes where the production is more likely to come from, and where other areas you've actually stimulated fractures, but they won't effectively add to the production cycle itself. This is an example from the Marcellus in northeastern Pennsylvania. I'm sorry, in Pennsylvania. And what we have here is basically, and it's fairly faint on the screen here, but a series of wells that cut across fault structures. And so here I have two wells, well A, that basically crosses this fault, and it's basically along the slope of one of the limbs. I have a well B that basically is down the flank from the fault. And what I've plotted here are those fractures, as we determined from the inversion, from the multi-tension inversion. And you can even from back here see that there's a difference in the type of pattern of activity we're seeing. We see here a whole series of a lot of smaller fractures, the dimensions are smaller, and a lot of subvertical fractures. Here you can see a lot more of these sort of rounder features, and these are much more sub-horizontal. In cross-sectional view, you can see that pretty clearly. There's a few subvertical fractures as you move up, but down here there's a lot more sub-horizontal fracture. Here you have a lot more subvertical fracture. So the question then is, how important are pre-existing fractures to the stimulation program? So you remember back in 2000, the concept or idea was that there are no pre-existing fractures in the reservoir. So now we're looking at fractures through the microseismicity, knowing they're fractures. Engelder and his group down in Penn State have done extensive mapping of the Marcellus, and they defined 3 fracture sets or joint sets. They've labeled them joint 1, and joint set 2, and a sub-horizontal set joint 3. So in my data set, go back for a second, I had well A and well B, and the 2 color codes here are 2 different stages that we've looked at in terms of the data. I now look at an equal area staring at distribution of the poles to those planes in the previous image. And it's pretty clear that for stage 1 in well A, there's one dominant set of fractures that are being observed. And that's this white line here. So we have a fracture set that's northwest, southeast, kind of moderately dipping. If I look at stage 2, there's actually one major set which lines up with stage 1, and a secondary, smaller defined set, stage 2. I'm sorry, the secondary set. What I have also mapped on here are the joint sets from Engelder. And what we can see here is, within pretty good reason and approximation, what we're doing in the stimulation program is we're activating that pre-existing fracture network. And in fact, it turns out when you go across all the unconventional plays in North America, and you start looking at this sort of detail, you find out that pre-existing fractures dominate in terms of the stimulation program, what's being stimulated in the program. Interesting as we move to well B, which was down the flank from the fault zone,
we end
up with one set that's dominates, and that's a subhorizontal set. And I haven't mapped on their joint 3 because joint 3 in end-gilded work has no set orientation. It's very variable. But we're finding basically along the flank, in one direction, one subhorizontal fracture set, which is really associated with the bedding plate. So now we have to start thinking in terms of how important that is in terms of potential production. Well, it does turn out that these subvertical sets, even stimulating them, results in better production than stimulating these subhorizontal bedding plane structures.
I give
another example here from the Barnett Shale. And in the Barnett Shale, again, here's this is down in Texas. We have some observation wells. We have a couple of stages that we're looking at in 2 treatment wells that are being planned out here. And here you can look at the map in terms of the event locations and here in terms of the actual fracture planes. And if you look closely, you can see that there's quite a variability in terms of those fracture planes as well, just like we saw in the last case. Look at it this way, it's hard to really assess what it is that we're looking at in terms of any trends. But we can start looking at it more carefully. So again, the wells, the treatment wells, we had 2 of them, and we had stages A, B, C, and D. These are called perf clusters. So in a perf cluster, it's a number of actual points that they're actually breaking into the rock at. So here we have a 4 perf cluster. So you have 1, 2, 3, 4. Whereas down here you have a 3 perf cluster. 1, 2, 3. So it means that they're trying to pump the same amount of energy into the rock through 3 perf spots, or 3 rather than 4. So if you start looking at the mechanisms and the failure orientations, and these are just rosette diagrams showing the orientation of the fractures. For the 4 perf ones, we can see out here we have a dominant fracture set. We have a secondary set that comes in and sometimes disappears, but basically you have one dominant set. This sort of behavior, where we have a random orientation, is right next to the treatment well. So that's what you would expect. You would expect at the treatment well, you have such a disrupted stress strain field that it would cause multiple types of fracture. Those fractures are probably induced by the actual stimulation itself, rather than being associated with pre-existing fractures. If I move down to into the 3 perf cluster, we have quite a change in pattern. We don't have one particular set that is failing. I've mapped down here the 2 types of fracture orientations that have been identified. So this is the pre-existing fractures. What we have here is the core drilling induced fractures, which is basically the fracturing that's been in place in the current stress field, and the core natural fractures, which were placed in the paleo stress field. So that is the natural fracture set in that site. And so if I look at those 2 orientations, you can see that northeast southwest orientation is northwest southeast. They very, very much closely align in some of these cases with the natural fractures. So we are definitely inducing fracturing associated with the natural fracture system. This is quite different. And if I look at the other 3 perf ones here, I have a similar pattern. So you can see that it's been a very disruptive type failure process, which generate a lot of new fractures that aren't necessarily associated with the pre-existing fracture network. So it gives a potential for the engineers to actually control the type of stimulation program you have. They did something interesting as well here. They did something called a hesitation fracture. And a hesitation fracture is when they actually pump into the reservoir for a period of time, and then they stop, and then they pump again. The concept behind it is that you're going to go in and stimulate a certain fracture set, and then when you stop, the stress is realign themselves or change appropriately, and you activate a secondary set of fractures, thereby increasing the fracture complexity, which then creates more opportunities for pathways for fluids to get back into treatment. The type of failures that we see, again, you can see here in the top left, you have that same sort of top right, shear tensile type failure behavior. In this case here, you can see a lot of closure of fractures. So as quickly as you're opening up fractures, you're closing them up. In some of these other stages, you actually have a lot more effective programming. You have a lot more fracture opening that's occurring. When you get to these 3 perf type clusters, it is quite a dog's breakfast in terms of what you see. But again, dominated by fracture opening components. And so that means that you can start looking at the type of fracturing and how effective that will be in terms of your ability to produce in those zones. The fracture reorientation, the hesitation frac, well, there's 2 instances. One of them actually on the left here was really quite interesting, is they had a pressure spike. And just by having a pressure spike, it's enough to change the local stress conditions and reorient the principal stresses so that you could actually cause failure to occur from one fracture set orientation onto a secondary fracture set. And so you're actually moving here from one pre-existing fracture to another fracture. And this is that hesitation type fracture on the right here. And this period here was a shut-in period. So you can see here the injection data, they stop. And then for a period of hours, you don't initiate again and they start the stimulation program again. So again, they're injecting at a certain pressure. And what you end up with is these sort of patterns in terms of distribution, dominance of one orientation or another sometimes. It's really hard to tell here if this is effective or not. And what is that? How do we know if it's effective? Well, one of the things I can do is, and this is just one of those stages, is I can actually look at that pre-shut-in period and post-shut-in period and the type of failures that we're seeing. And if I look here in this pre-shut-in period, this fracture set is dominated by a shear, has some tensile opening component. This one here is dominated by more of a closure type failure process. And so you start seeing the fact that certain fractures are changing behavior. Going to the post-shut-in, this fracture set here stays going from more shear tensile failure to an opening type failure, so opening these up. These, again, stay pretty much shut in. So it does offer the opportunity to be able to look at that and be able to say how effective these fractures are in terms of increasing potential productivity associated with these stimulation programs. So all this has been based on looking at microseismic data. No one who's been doing hydrofrac monitoring for many, many years ever believed that they're putting enough energy into the earth, into the ground, to generate any events of any significant size. So all the instrumentation that has been put out there has been looking at the concept that all events have magnitudes less than 0, small events. Well, we actually start looking at the data in detail, and here I've shown 3 different sensors that are used. 15 hertz are typically used in all these operations, and the spectral response associated with that. And when this is actually for quite a large event, so it's not probably the best example, but in this case here, if I look at that plateau, that can be related back to the magnitude, and in this particular example here, that's a magnitude 0.8. If I go to a 4.5 hertz phone and actually incorporate that low frequency, measure that low frequency energy, that actually turns out to be a 1.8. And so what happens is that in these areas here, we have no signal, and so we're actually biasing the system. And for many years, people believed that by monitoring the 15 hertz sensors, we had only small events. In actuality, we're generating larger events because of this effect that's referred to as magnetic saturation. And actually, if I get down to utilizing an accelerometer, which goes all the way down to 0.1 hertz, the actual magnitude of the event was closer to 2.3. So 2.3 versus 0.8, it translates down. If it's 0, it's 0 would be like a -1. That's the quarter for showed. So we're underestimating the magnitudes. And when you start underestimating the magnitudes, you have a misrepresentation of what's going on. Because if you think these are all small magnitude events, then the dimensions of the actual fractures are small. So you have a dimension of a series of fractures that may or may not be interacting or intersecting each other. If you actually have large structures there, then you're generating larger events, you have larger dimensions, and they can have a more profound effect on the actual stimulation program. If I take what typically is a fracture, you see the microseismic level, we're talking about something that has a dimension of a few meters to a few tens of meters.
Now I'm going to replace that by saying we have fractures in there that are also hundreds of meters in size. And so
what is that going to do in terms of your production? Is it going to enhance your production? You have more potential surface area for fluids and to propagate along? Or is it actually going to take production away from the zone of interest? So going to the Horn River Basin is just an example. We start putting in these surface networks, and this has only been in the last 3-4 years that this has occurred. And in putting these your surface networks, we start looking at these lower frequencies and picking up all the energy associated with these events. And all of a sudden, we start seeing a lot of events with magnitudes above zero. And in fact, in this particular example, this is over a period of about 3 weeks. They were stimulating both sides of this pad. We call it a pad. So these are all the treatment wells in red. It started stimulating this side and then went over to this side here. And actually it's over 60 days. My apologies on that. And what you have is a whole series of events that are occurred above magnitude zero, almost over 1,000 of them. And those, with the microseismic system using high frequency sensors, would have all appeared to have magnitudes below zero. So now all of a sudden, magnitude 3, you're talking about something that has a dimension of about 700-800 meters. And now that's being put in the middle of your reservoir. And that definitely has a potential effect. On the right here, I have that KT plot. You can see that they're dominated by a shear tensile type failure process, so that nothing extraordinarily new there. It makes sense. And here, these are the poles to the plane, to all those plane orientations. And you can see that there's one dominant set here, and then there's probably two subsets associated with that as well. Interestingly enough, you can see the distribution of events here. You have one set that goes in this orientation, another set in this orientation. Hard to pick any orientation out from the north side of that pad. So you have some structures, larger structures that are coming into play. So what's going on in order for these different structures to be activated? Well, one of the things that's happening is, of course, is that the stresses and strains are being modified by the injection program. And what I have here is the maximum, intermediate, and minimum principal strain orientations. And I can look at the three different sets. We have one set, we go to this second set, and we move into this third set. And we have a transfer going from one structure, one fault structure, to another fault structure. And in that process, you can see how the principal strain axis is here. It's a northeast, southwest orientation. It's rotating around and becoming slightly subvertical. And I look at the intermediate stress. It's not too bad in terms of the orientation. It's fairly stable. But the minimum principal strain is quite dramatic in terms of its, particularly during this stage here. So what we have is the control of these stimulation programs is not just based on the regional stress field. It's based on the fact that we're modifying the local stresses and causing, allowing different fracture sets and fault sets to actually be stimulated and move. Also, by doing that, by monitoring these larger structures, all of a sudden theory makes sense. This is actually a distribution of the size of event, the size of moment versus the corner frequency or the source radius at the top of dimensions. If you take data from all over the world and you start plotting it, you're going to find they all kind of fall in this sort of an area here. And these are stress drop lines, so the amount of stress released over different magnitude scales. And this is referred to as a self-similar behavior, saying that the fracturing pattern associated with small events, the way the fractures occur, is also the same way the larger fractures occur. So the mechanisms or underlying physics of the fracturing process is the same. The one unique thing about hydrofrac data is, as shown here in the red and green circles, is that they tend to be on the lower side of all the stresses that are observed in all these other domains. And all these other domains are everything from natural earthquakes to mine-induced earthquakes to nuclear explosion-related earthquakes. So the interesting thing about these hydrofrac events is that the fluids play a very important role. And because of that, they're almost like the stress release is a lot less, and so you effectively have almost a
frictionless, not quite frictionless, but friction plays a lot less role in these fractures than in all these other fracture types. And that again plays an important role, because if you can understand that, and you start looking at these sort of behaviors, and you start getting events that have higher stress releases, and you may actually be activating events away from the actual treatment zone, or ones that are less influenced by fluids. So then you can start looking at these fractures as being either stress-related fractures or fluid-induced fracture. So where is this all heading? So we started by the process by saying that we had a single subvertical bi-wing symmetric fracture around the treatment well. It's pretty evident that fractures have a lot of different orientations. It's pretty evident that pre-existing fracture network plays a role. We can't think of this as a single sort of fracture in that orientation. Early work in the 80s from Pine and Batcher and others suggested that, well, maybe we do have fractures, but they're all evenly spaced, evenly gridded, and so we can create a network of fractures like that. And we can try and model that and be able to come up with some representation of what's actually going on. Well, now we actually have the actual fracture orientations, and so we should be looking at those distribution of those fractures to see how we can develop those models better. One of the things that's, if you look at the distribution of one of the input numerical models or geomechanical models in terms of trying to develop an understanding of how these stimulations actually progress, is to look at something like the power law distribution. And if on the left I have their work by Rennie and Dunphy, they normally have you incorporated 3 data sets, core log data, outcrop data, and seismic data. So seismic's easy enough. People go out and do 3D seismic surveys all the time. You can from that get a certain size scale. Well, most grid scales on seismic surveys are at least 50 meters to 100 meters in size. So you're not going to be able to actually image anything less than 50 to 100 meters in size. Now, I said earlier that the fractures that we're looking at from the microseismic scale are order of a few meters to a few tens of meters. So it's missing that component. Outcrop data, a lot of these petroleum environments, you don't have outcrops. Again, I'll go back to Horn River. Horn River, they have for their reservoir, they have a single outcrop they looked at to make decisions on that was 50 kilometers away from the actual wells that are being stimulated. And core log data, again, you're looking at fine, small scale fractures of the size of a core, and so that doesn't necessarily give you a full representation of what's going on. The scale of interest that they're most interested in here is where they have the least amount of data. And so that's where, by using the fractures that we get from the microseismic data, we can actually work out what that discrete fracture network power law distribution is. And so I can look at that distribution of those fractures and incorporate that with the other data to come up with a better representation of the distribution of fractures. Then you go into a numerical model. So this brings me to where we are now. So where we are now is trying to understand how we can take these fractures that we measure, we identify, and incorporate them into a model, and incorporate a model that's going to be a fairly effective representation of what's actually going on in the reservoir. So I can start off. We start off with looking at a very statistical approach, and I'm not going to pronounce his name because I get it wrong all the time. It's Sofolahi. It's all his algorithm. It's based on his work, and in his work, it's basically a statistical routine. We can take in there a series of event locations, and at every event location, randomly allow this program to go through and assess an orientation for the fracture and plot that up. And so what I've done is, for a series of events that we recorded for a stage, we actually plot the distribution of the fractures. And here are 2 runs using the algorithm, and basically we end up with no concerns. And you effectively have a completely random set of fractures that we generate. Here in the middle, what I have is the actual defined discrete fracture network for this particular stage. These are the orientation of the fractures that we measured, we determined from the microseismic data. Using these as inputs, we basically then optimize the program And from that, the program will come out with a series of distribution of fractures for those particular events. And those, we find that the algorithm is actually replicating pretty closely the actual observed orientations that we see. Then we did something referred to as a crippled SMTI plus optimization, where we effectively took a subset of 10 to 15% of the data and tried to see if you could replicate what was going on. So in that process, we could see it did fairly well in terms of replicating the actual data we have. This is the first step in terms of being able to take this sort of data and be able to come up with a modeled approach to that's calibrated model approach that can be used in terms of putting into a reservoir program to see how your stimulation program will be affected by the presence of these fractures. The upshoot of this as well for the other side is that when we do the inversions of the actual fracture orientations, it's very difficult to actually look at all the data. In that Horn River example I've been showing you, in that 60-day period, there were almost 250,000 events that were actually detected and monitored and recorded. There's no way that anyone could sit down and go through that and determine a fracture orientation for all of those fractures. We actually did it for about 70,000 events, which is a tremendous feat in itself. And from that, we now have an understanding of how these 70,000 fractures behave. But we know that the additional 180,000 or whatever events left, we don't have determinations for the actual fracture lanes. Those events are actually associated with fractures themselves too. So how do we actually go from the 70,000 to the 250,000 events by affiliating? And the only way to do it is statistically. And that's where this crippled SMTI type approach is showing we can start with a subset of known fracture orientations and build that out to represent on a larger scale what's going on in the reservoir itself. And now what you have is a complete fracture network that has been actually stimulated by the injection program. And an understanding which proportion of those have opening components that's fairly associated with them and which ones don't, and which ones can thereby contribute to the actual stimulation. So that's where we are today. That's where we're moving forward on in terms of the development cycle of the science, of the technology. Basically, it's trying to link the geomechanics, link the microseismic data, link the seismic data we have to simulation workflows. And what we're trying to work on, what we're working on is this fracture interface. And that basically will go into a reservoir flow simulator that will allow us to effectively work out what the flow regime is associated with these stimulation programs. And that then allows you to move forward with the concept of developing an integrated surveillance program associated with these stimulations themselves. You work out you go in there by doing microseismic monitoring with the completions program. You get the event location, the fracture maps, source mechanisms. I didn't talk about EFF maps. And from that, use that in various models to develop a forecasting process that allows you to basically carry through, develop what you think would be the distribution of areas of potential production, and then match that to production history itself. So we start out with initially a decline in production curve associated with symmetric fracture. Say that fracture is important, we change the decline curve. The whole aspect of looking at hydraulic fracturing is to understand at the end of the day how to stimulate the rock to improve your production and hopefully at the end of the day improve your reservoir estimates, your estimate of the reservoir size. So to summarize, last decade or so, microseismic monitoring has been certainly used to enhance our understanding of hydraulic fracture. As I mentioned here, structure was very important in the early days, particularly in shale plays and conventional plays. Moving away from that bi-wing fracture model has been torturous for engineers. But at this stage, we are now 15 years later, there's an understanding that has to be moved forward in order to understand reservoir behavior. Extensive rate coverage, advanced understanding of event signals has allowed for all these aspects related to mechanisms and failures, we're seeing opening versus closed fractures, assessment of natural fractures, how important they are in different stimulation programs, the role of bedding planes and how ineffective they are towards stimulations. Targeted injection programs allow them to target specific volumes, be able to improve their production. And refined estimates of enhanced fluid flow or it's stimulated reservoir volume. If you know that certain fractures are intersecting and you have a high complexity fracture network there, then you're going to get your production from those volumes. Areas where you have fractures that are closing, that are not connecting to each other, you're not going to get much production there. So ways to be able to refine that estimate is very important. And as I said, moving forward, basically, using these sort of integrated approaches between surface and downhole monitoring, linking geomechanical models through the use of microseismics to basically calibrate and validate those models is the direction things are going now. And you'll see out there, if you are looking at this in the near future, the incorporation of microseismic in these models is going to be more and more prominent. And ultimately, putting all the pieces together is what's being done to more and more accurate reservoir models. That's the end of it. I just want to acknowledge that over the last number of years, there's quite a few people that have been involved in terms of the research and development. And here's just some of the names. We've actually, over the last few years, put out over 150 publications on different aspects from as so nicely put in the very beginning, in all these different areas, from rupture dynamics to source mechanics to the practical application. And so you can look for any of these names out there, and I'm sure you'll find a lot of information in detail. And with that, I'll leave it for questions and this beautiful Dylan comment from a couple of weeks ago. Thank you.
Thank you, Ted. So we have some questions from the audience. I'm sorry.
Can you get the best data under my tracking sometimes? But then, of course, forecasting is useful. So, how much development do you need? How early in the development stage can you get actually enough data out to do useful forecasting?
Most of the forecasting is not based on a single well. You're not trying to. If you're doing a stimulation of a well, the purpose of that is to make sure that the fractures are contained within the reservoir, and that you're not interfering with any sort of geohazards, water-bearing layers. So that's what you can do in real time in terms of forecasting what may happen with doing stimulation. When we talk about forecasting, you're taking a field area, which could be a few hundred square kilometers, and over that field, putting out a whole series of wells. It could be literally hundreds and hundreds of wells. So the forecasting we're talking about here, you start out with a series of treatments. You collect the data, you understand the process going on, and you apply it to the next series of wells, and you keep that process going. There's nothing more than, and I don't know how many engineers are in here. They're not turning them, putting a damper on them. But the simple approach is, engineering approach is, if we can do it once, we just have to replicate the same process all the way through the entire field. Well, geology isn't like that. It's variable from one site to the next. And even in the images that show from one side of a pad, we had a series of wells to the other side of the pad. The response will be quite markedly different. And so understanding what your fracture network is doing, how it's behaving, gives them some insight to the ability to be able to stimulate the next set. So forecasting from that perspective makes sense. Forecasting while you're stimulating, it may happen someday, but it's very doubtful at this stage. The data that we're getting from there is not something that comes out in real time. event locations, source mechanisms, no. Source parameters, magnitude, stresses, yes. Can we find a proxy for source mechanisms? We keep trying. We haven't had any success yet. If you could, then you could do something in real time. Not now.
Okay, any more in the room?
Thanks very much for making the effort to come all the way to Toronto from wherever you last worked to provide this lucid overview of the ever-expanding art and science of microseismic monitoring. I think many in both your actual and virtual audience may not appreciate the scale of microseismic in the geophysical industry, which I'm going to surmise just from the impressive growth of ESG has gone from maybe a $5 billion industry to a $500 million or $1 billion industry.
I'd say right now in North America it's about a $250–300 million a year industry. That's going from zero in 2000. Still having said that, probably only about 5% of all wells that are drilled are actually monitored. So there's a lot of more expansion capabilities. And that's not including anything worldwide. The rest of the world is just starting to pick up on the technology itself in the Middle East and Argentina and other places. And so the pervasive technology is just going to go through the roof.
And I would further observe that the microseismic monitoring is a fairly conclusive way of demonstrating that the fracking are greatly exaggerated in the sense that you can see how limited a distance the fracturing actually influences the rock mass.
Yeah, I mean, from the public perspective, I mean, basically these fractures, the largest events, well, actually Fox Creek in Alberta registered a 4.2 in the fall. That's pretty much the largest you're going to have. You're talking about a fracture that's about a kilometer, 1.2 kilometers in dimension, but you're down 3+ kilometers in depth. And the influence in terms of groundwater is going to be highly unlikely. In terms of influence of shaking on the surface, you have a little bit of shaking on the surface, but most of the events, and from the distribution I showed from magnitude 0 to 3, that's more typical. Typically we have magnitude 1, magnitude 2, the odd 3. There's not going to be much ground movement at surface as a result of that. So from the public perception side, it's good that they're monitoring. They should be monitoring, so they understand what's going on. But it will have little effect. It should have little effect on the environment itself. From the client or the company side, monitoring of these seismicity is very important from a more engineering perspective to understand the size scales that you're actually simulating, what are the fracture sets, and as is indicated there, that distribution of fractures is part of that power law distribution. Now we're looking at fractures that transcend 6 orders of magnitude and 6 orders of sizes. So it's important to know that that's what you're doing or else what's going on in your reservoir if you're going to design an effective program, recovery program.
Thanks. And one further historical comment, going way back, even before your start of your illustrious career, people were monitoring natural microquakes in geothermal systems in wells with very little understanding of the source mechanism, I would say.
Oh yeah, I mean, monitoring of seismicity has occurred for many, many decades in all sorts of different environments. Even going back to mining environments, people were monitoring that since the 1930s and 1940s at one point or another. A lot of the work that ESG has been involved with started out working with the mining industry, looking at rock boards and fracturing associated with mining excavations. So it's not new. What's new is the level of understanding of what these fractures are doing, the type of fracture we're seeing, their orientations, how they interact, how they behave under different circumstances, under different stress strain conditions. That's all new in terms of these hydraulic fracture stimulations, and also its application in other environments. So the envelope is being pushed every day in terms of understanding, which is a really good thing.
Okay, Elizabeth has some questions online.
There are 4 questions online. The first one is from Joseph Islas. Were the interpretive fracture maps based on field investigations only, or was there a remote sensing component?
The interpretive maps, maybe talk about the statistics. Basically, it's based on real actual field data.
The next question is, was the principal fracture strike orientation a determinant in horizontal wellbore orientation?
So most treatment wells, all treatment wells, they go in with the idea that basically they're going to be perpendicular to the maximum horizontal stress orientation. And so that would suggest that the fracture row and SH max would be perpendicular to the treatment well.
The next question is from Sergio Espinosa. He is asking, using routinely 3D seismometers on surface and in boreholes? Sorry, let me check that. I'll start again. What are the costs versus benefits of using these?
Using those sensors?
Yes.
Well, all the sensors that we use are 3 component. So they're all 3D or 3 component sensors. So they're measuring all the entire energy field from every orientation, whatever single orientation you can. The benefits of it are, well, everything you see here, much better understanding of what's going on in the reservoir and what the stimulations are doing. If you're using a single component, you only measure part of the energy field, and you really couldn't do services other than location, other than locating events.
One last one from Bruce Smith. He says, has this type of monitoring been applied to studying induced seismicity from injection wells?
You mean from wastewater injection wells? Yes. I believe you say wastewater injection wells. So that is something that is a real prominent area of monitoring discussion now, particularly in the public domain. A lot of the wastewater and waste products that come out of these injection programs get re-injected into the ground. And these wastewater injection wells have been associated with events all the way up to 95.2. There's questions as to whether these events are actually associated with pre-existing fractures or faults in the area, or if they're actually being induced by the injected put into the ground. There's debate about that, what's going on ongoing, but in fact there are quite a few induced events associated with these injection wells. Particularly in places like Oklahoma right now, and what's really interesting there is the USGS put out their US seismic array. I believe it's about 250 stations around these areas, so in the next couple of years, there's going to be some fantastic data coming out in terms of understanding these injection programs.
And people are generally reducing the volume of being injected, I think, too.
Well,
sensitivity.
Yeah, that is the hope, yeah. We start monitoring national seismic effective systems, but if monitoring, we're not sure what we're doing. So it's very simple. We actually have a waste monitoring program in California for the city of Los Angeles. It's the biggest human waste disposal system in the world. So we're actually injecting human waste into the Urbancic reservoir to try and produce methane at the other side. So one monitoring that injection program. So there's all sorts of things going on.
Any more questions in the room? All right. I'll want one that you just gave us.
So from my understanding, also the way to monitor the fracture is basically using the force motion, but nothing to do with the waveform motion issue. And then the second reason is that how accurate we can know about the fracture. I mean, includes the fracture location and the fracture length scale. Is there any quantitative criterion of that?
Yeah, so there's, you can either do a forward modeling approach or an inversion approach. The inversion approach would use amplitude information as well as the first motion that you indicated there. And as long as you have a good three-dimensional distribution of sensors around the volume of interest or target itself, you can get a fairly good representation of the actual orientation of factors. In terms of validation of this, this has been, the techniques and approaches have been validated through earthquake seismology for decades. It's also been validated from work we've done or that's been done in mines. We can actually go physically underground and look at the actual fracture that has been activated. And so the correlation between them, you probably have, if you have a good distribution, you can have accuracy in terms of orientation of plus or minus 10 degrees of fracture in terms of the strike. Dips probably 10 to 15 degrees as well. So we have fairly good control, and there's fairly good evidence out there that fractures that we're identifying through the inversion approach actually represent fractures that are actually being stimulated or activated.
Anyone else on the line? No. Okay.
Okay, well, thank you.
Thank you very much, guys.
You're welcome.